Welcome. Today we'll explore two fundamental linear transformations, rotation and diagonalization. Let's start with rotation matrices. A rotation matrix spins vectors around the origin without changing their length. Theta is the angle of rotation. Let's see a specific example, rotating by 45 degrees. Watch what happens when we apply a rotation. I'll show you a grid of vectors being rotated together. Here's our original vector pointing to the right. Now watch it rotate 90 degrees counterclockwise. The key property: rotation preserves length. The vector is the same size, just pointing in a new direction. Rotation matrices have special properties that make them unique and powerful. Property 1. Rotation preserves vector length. No stretching or shrinking, only spinning. Property 2. Rotation preserves angles between vectors. The entire space rotates together rigidly. Property 3. The determinant is always 1. This means area is preserved during rotation. Property 4. Rotation matrices are orthogonal. Their inverse equals their transpose. What happens when we rotate twice? We can compose rotations by multiplying matrices. Example: rotate 30 degrees, then rotate another 60 degrees. The result is a single 90-degree rotation. Now let's explore diagonal matrices. These are much simpler but incredibly powerful. Notice the zeros. All off-diagonal elements are zero. Only the diagonal matters. Here's a concrete example, a diagonal matrix with 2 and 3 on the diagonal. Let's see what a diagonal matrix does visually. It scales vectors along the axes. Original vector at position 1, 1. After applying our diagonal matrix, it becomes 2, 3, stretched along each axis. Notice, x-coordinate scaled by 2, y-coordinate scaled by 3. Each axis scales independently. Here's where diagonal matrices really shine. Computing powers is incredibly easy. Compare this to rotation. Computing r to the third power means rotating 3 times, which equals 1 rotation by 3 times theta. Let's directly compare rotation and diagonal matrices side by side. Rotation matrices spin vectors while diagonal matrices stretch them. Rotation preserves length. Diagonal changes it. Both are useful. Rotation for rigid transformations, diagonal for independent axis scaling. Now let's see how to implement these in Python using NumPy. Here's how to create and apply a rotation matrix. Import NumPy, define the angle, and build the rotation matrix. And here's diagonal matrix code. Much simpler. Just create a diagonal with your scale factors. Let's recap everything we've learned about rotation and diagonal matrices. Thanks for watching. Practice with these matrices in Python. Happy transforming!